Hello everyone, we've got our video on sampling distributions today, which in itself is not necessarily important, but it is the foundation of everything we're going to see from here on out this year. So try to pay attention and take notes on this one. So just a review for you guys. A key distinguishing feature between what we're going to talk about is you need to know the difference between a parameter and a statistic. I will remind you, a parameter is something that comes from our actual population, so the entire large group that we're interested in. So for example, for the average height of all Americans, we wouldn't use X bar, we would use mu, okay, that kind of Greek letter mu, and that is that true population mean. Whereas if we looked at a small sample, that's called a statistic. So statistics represent samples, parameters come from our population. So for a proportion or a percentage, the percent from a sample is called our statistic, or p hat. And then the parameter for our population is just a p. Okay, we can see the same thing with standard deviation. For our population, it is sigma, and for our sample, the statistic is S, and we don't really deal a whole lot with correlation. So what we're really after in sampling distributions is this idea of the central limit theorem, okay? And specifically, to start off, we're going to talk about it with regards to sample proportions or percentages. We can do the same thing for means, but for our first lesson here, we're going to talk about proportions. So let's say that the true proportion of Americans who exercise regularly is 68%. In other words, if we took every single American, P, or the true proportion of Americans who exercise regularly, would be 68%, okay? Then if we took random samples of size n, whatever n is, maybe it's 10, maybe it's 20, what would you expect those p hat values to be, or what would those sample proportions be? And you'd probably think, well, they're going to be around 68%, but they're probably not going to be exactly 68%. Maybe 65 for one of them, maybe 72 for the next, maybe a couple are actually 68, but it's not likely that every single one of them is going to be exactly 68, okay? But once we take each individual sample and the proportion or the p hat from that sample and put them on their own distribution, this is what we refer to as a sampling distribution for a sample proportion. So when we take each of those individual sample p hats, so the proportion from each sample, and we put them on a distribution of their own, it turns out that we would expect that histogram of the p hats to center around the true population parameter, that p value of the population, okay? So even though we may not have known going into it that the actual percentage was 68%, if we put all those p hats together, we would imagine that they would center right at 0.68, okay? Additionally, when we put all these p hats on a separate distribution, it is going to be unimodal and symmetric, and it will be centered at that true proportion value. More specifically, we can use a normal model to actually represent or estimate the sample proportion distributions. And this is what we refer to as a sampling distribution. So let's just say, for example, that we took numerous samples of size 20. So we had 20 people in one sample, 20 in the next, 20 in the next. And then from each of those samples, we took the percentage of people who exercised regularly. Then if we were to put each of those individual percentages on a histogram, which we see here, we see that this is very well centered at 0.68. And that's exactly what's going to happen all the time. So we see that there's a higher frequency in that middle portion, that 68%, and it kind of goes off to the side similar to a normal curve, okay? So even though not every sample is going to be a normal or approximately normal distribution, when we put all those sample proportions together, it is approximately normal. So when we can, we love to use the normal curve because we have some really useful characteristics of that normal curve. For example, we have the normal CDF, normal PDF, all those good calculator functions. But we also have that 68, 95, 99.7 rule. So if we have a sampling distribution, we can use the normal model to approximate it, okay, with a mean and a standard deviation, okay? So the center or the mean of our normal curve is going to be the population proportion. So whatever that true population proportion is, that will be the center of our distribution. So for our first example, we would be centered at 0.68, okay? Then the standard deviation, we almost never know exactly what that standard deviation is going to be. So we can estimate that standard deviation with this formula. It is the square root of p times 1 minus p, or q, divided by our sample size of 20 in this case, okay? And just as a notation, we could say that we have a normal curve centered at p, standard deviation of square root of p, q over n. So if you're more of a visual person, you see here that we are centered at p, our population parameter, or population proportion, excuse me. And then we have the standard deviations estimated using that square root of PQ over N. So very nice normal curve. And this is always going to be the case for a sampling distribution. So just like with any normal curve, the 68, 95, 99.7 rule is still going to apply. And like I said before, within each individual sample, we're very seldom going to have exactly what that population proportion is. So you're not going to get 0.68 out of every group of 20. Maybe you get 0.65, 0.62, 0.72. So you're going to be off by a little bit. And that's what we refer to as sampling error. Okay. But again, as we take more and more samples, it will start to form right around that actual population proportion. So before we dive into assuming that a normal curve is appropriate, we do have some assumptions and conditions that we have to check. Okay. So most models are only useful if specific assumptions are true, and this is exactly the same case with our sampling distributions, okay? So two assumptions that we have are the sampled values have to be independent of one another. So when we take a sample of 20 people, those samples have to be independent. Also, we have to talk about sample size. So we can't have a sample size that is too large or too small. So we kind of have to find a middle ground there. So these assumptions are very vague. In practice, what we do to check these assumptions is actually look at some conditions, which I'll outline next. So before you dive into using a normal curve, you have to check these three conditions, and these three conditions are going to come up an awful lot here in the next couple of units we go through, okay? So the first one, we have what's called the randomization condition, meaning that each sample that we take has to be a random sample, okay? We can't just pick our 20 best friends, say how many of you exercise regularly, then go to our next 20 friends. We actually have to do a random sample of our population. So oftentimes in the problem, it'll say we took a random sample, so that's almost always going to be good to go. Then we have the 10% condition, and this is what verifies that our samples are independent, okay? So the way we check that is that our sample size, or N, the number of people within each sample, can't be any larger than 10% of our population, okay? So if we have 100 people in our population, that means that our N could be no more than 10 people, because 10 out of 100, that's 10%. So at most, we'd be able to take 10 people in our sample, okay? Obviously, the bigger your population, the larger the sample you can take. And then our third condition is the success failure condition. And this is actually what's going to verify that we have a big enough sample, okay? So the 10% condition says we want it to be not too big. Success failure says that our sample can't be too small, okay? So what we have to have here is that the number of successes and the number of failures within our sample has to be at least 10, okay? So in our example about exercising, we need at least 10 people in each sample that exercise regularly, and then we need at least 10 people who don't exercise regularly, okay? So if these three conditions check, we can use all of the properties of the normal curve. So you might be wondering, why in the world do we go through all this work of figuring out sampling distributions? Simply looking at one sample and finding that proportion is fine, but it is just one sample, okay? So you might get a sample with very few people that exercise or a ton of people. It may not be representative of the entire population, okay? And if obtained appropriately, the properties of the normal curve can be used in a sampling distribution. So again, we want to use that curve anytime that we can. So one thing that I want to expand on is the idea of sample size, okay? We've talked about how sample size has to be less than 10% of our population size, but within each sample we also need to have 10 successes and at least 10 failures, okay? So what do we see here? Let's first talk about rolling a die, okay? So if we were to take a die and toss it 10,000 times, this is about what the distribution would look like. And it's not very insightful, is it? Okay, it's kind of uniform, flat. We don't really have much shape to it, okay? Well, let's go ahead and expand the sample size. Instead of rolling one die, let's expand that and see what happens. So on the left here, we have the distribution of if we were to roll 2 dice and then take the average of the 2 dice, plot that on here, we see that we have a much more defined bell shaped curve, but still our range is pretty spread out, okay? So if we look at the right here, we're rolling 3 dice, and then we're going to take the average of the 3 dice and plot them here. Do you kind of see how it's getting more centered at that 3.5, and it's also getting less spread out as we go? Let's see what happens when we expand from 3 dice. On the left now, we are now rolling 5 dice, and we're taking the average, and we're doing that 10,000 times. The corresponding histogram of that, very much bell-shaped curved, okay? We see a very clear bell shape, much more centered at the center there. And then if we took 20 dice in a single sample, and then took the average of the 20 dice and then tossed it 10,000 times, we see that we have a very, very well-defined bell curve, and we hardly got any spread whatsoever, okay? So in general, what do we notice? As our sample size increases, our curve is going to get more and more normal shape. So like I said, as our sample size gets larger for each of our samples, so as we went from 1 die to 2 dice to 3 dice up to 20, as that number of dice increased, we saw that the center became closer to that actual mean of 3.5, okay? And then it also became more of a normal shape. So in general, as our sample size increases, that's going to be a good thing, so long as we aren't violating that 10% rule, okay? It's going to become a more well-defined, more refined normal curve. And this is actually a perfect illustration of what we refer to as the fundamental theorem of statistics, or the central limit theorem, okay? So as our sample size increases, we get a more normal shaped curve, and it's going to be a normal curve centered at our population parameter, whether it's a mean or a proportion, okay? And this is true even if our original distribution was not a normal curve. So it's a really fascinating, really cool thing that happens in our sampling distribution. So don't get too hung up on this slide. Really what I'm saying is that exactly what we saw for proportions or percentages also will apply to means, okay? So if certain conditions apply, then by taking the sampling distribution with means, we will actually get a normal curve, and we can use the properties of the normal model. So for means, we also have a set of conditions we have to check before we can confirm that a normal model is appropriate. Just like before, we still have our randomization condition, so our values have to be randomly sampled. Again, that's typically going to be stated in the stem of our problem. We still have the 10% condition, so our sample size cannot be more than 10% of our population size. And then we have the large enough sample condition, okay? So the central limit theorem doesn't tell us how large a sample we need, but in general, if our sample size is greater than 30, that's typically going to be good enough, okay? And we'll expand on this in the future, but in general, if our sample size is greater than 30, we can just assume that it is a large enough sample. So once we verify these conditions, either for proportions or for means, we want to know what is the mean or the center of that distribution of the normal curve going to be, and then what is the standard deviation going to be, okay? I already talked a little bit about standard deviation for the proportions, but for proportions, the middle of our distribution is going to be the population proportion. So for our exercise example, that would be that 68%. That's going to be the center of our model. Okay. And then as you can see here, our standard deviation of P is going to be the square root of P, 1 minus P divided by N. Then for means, very similar. The center of our normal curve for means is going to be the actual population average. So if the average height is 70 inches for our population, our sampling distribution will be a normal curve centered at 70. And then our standard deviation is going to be the standard deviation of our population divided by the square root of n, or our sample size. Okay. And this seems a little intimidating, but once you get rolling with it, it really isn't too awful. And we'll see some examples here in a bit. So again, if you're more of a visual person, let's take a look up here. So on the top, we have our distribution of our entire population. Okay. Of course, for our population, we have a mean or an average, and we have a standard deviation. And as you can see on this top distribution, it is far from being a normal curve. Okay. In fact, it's very much skewed to the right. Our mean or the average is right on the left side. That's where our mound is. Okay. But when it comes to forming a sampling distribution, we are going to take separate samples, a bunch of separate samples from our population, which I have in the second line here, these histograms. And from each of those individual samples, we are going to have a mean. Okay. So you see here, I have y bar 1, y bar 2, y bar 3. Each of those individually is a mean from each of our samples. Here I've only got 3 of them, okay? But you would repeat this over and over and over again and get a bunch of samples, okay? Then in our third line, we are taking each of the individual means from each sample and putting those means on our distribution, which is this third line here. And as you can see, definitely more of a normal curve, okay? And if those conditions that we talked about earlier all check off, then we are able to use not this kind of rigid looking normal curve, but we can approximate our distribution using the actual normal curve, okay? So as you can see, going from our top line to our bottom line, we are turning a very non-normal looking distribution. It's very much skewed to the right, and we are going down to the bottom where it is very normal looking. So let me walk you through a couple of examples here. This first one has to do with proportions, okay? So for this example, we'll say 12.4% of mortgages were delinquent or foreclosed on in July in 2010. And suppose a large bank holds 1,731 mortgages, okay? First thing we want to know is, can the central limit theorem describe the sampling distribution of proportions in this situation? Whenever you see that, we are basically asking, can we use the normal curve to answer some questions about this down the line, okay? And to do that, we just have to check our conditions. So we have our P hat, or our proportion is 12.4%. And then we have our sample size of 1,731. And we want to know, using that, can we use the central limit theorem? Can we use our normal curve? So this is how we would go ahead and see, can we use that central limit theorem? We have to check the conditions. So first off, one delinquent mortgage does not influence the next mortgage, so we could say that they are independent from one another. Typically, we say it is safe to assume that the mortgages are independent from each other. Okay. Now, also, if we think about 1,731, or our sample size for this one bank, that is probably going to be less than 10% of all mortgages in the United States, okay? Oftentimes, you are not going to be given what that actual number of mortgages in this case is, but in the US, there's like millions of homes, so there's probably millions of mortgages. So we're pretty safe on that one. Then we have to take n times p, and this is where n times p has to be greater than 10. So in this case, 1,731 times 0.124, or 12.4%, is 214, which is greater than 10, meaning we have at least 10 mortgages that are delinquent. And then on the other hand, if we take n times 1 minus p, or n times q, they're the same thing. If p is 12.4%, 1 minus p is going to be 87.6%. And that gives us 1,516, which again is greater than 10, okay? So that means we have more than 10 mortgages that are delinquent, we have more than 10 that are not delinquent. So because all of these conditions check out, we are able to use the normal curve. So on that same example, given that the CLT or central limit theorem applies, which we just talked about, we might then want to sketch and label the sampling model using our 68, 95, 99.7 rule, okay? Basically, that just means draw a normal curve and use the 68, 95, 99.7 rule. So here, because we know and we check those conditions, we are able to approximate for proportions. We have a normal curve, so normal curve here. It is centered at our population proportion, which is 12.4% or 0.124. And we can approximate the standard deviation using this formula. So our P is 0.124, that'll be the center of our curve. And then if we plug in P, 1 minus P, and N, that will give us our standard deviation, okay? So let's take a look at what that would look like. So it is exactly what I have here. If you look here in the middle, that is our population proportion, 12.4%, so that's where we're centered at. And then we go out from about that standard deviation that we found, the 0.007 or whatever it was, okay? So if I ever ask you to check the condition or verify that the central limit theorem works, you're checking the conditions. And once it does check off, you can use the formulas to describe what that normal curve would look like. Another extension on this same problem. So we already have that the percent of delinquent mortgages is 12.4%. We have our standard deviation. And the bank owns 1,713 mortgages. We might want to know what is a safe range of mortgages the bank might expect to foreclose on. Okay, so we might want to know generally how many can we expect that the bank is going to foreclose on. Okay, well, basically we're looking for a range of values here. Now, if you remember, we talked about how most of our data, or 95% of our data, falls within 2 standard deviations of our mean, or in this case 12.4%. So we can find a low end and a high end for the -2 standard deviations and +2 standard deviations from that mean. So I'm trying to click here, sorry, there we go. On the low end, if we take 12.4% -2 standard deviations, that would put us at 10.8%. So on the low end, we'd expect 10.8% of our mortgages to be delinquent, and 10.8% of the total number of mortgages we have is 185. Okay, so that would be the low end estimate. Okay, but then on the high end, we would take that 12.4% plus 2 standard deviations, which is about 14%. So if we take 14% of our total number of mortgages, that would be 240. So altogether, putting the range of values together, we would estimate we're going to have about 185 up to 240 mortgages that will go delinquent. Our last example here has to do with averages instead of proportions. So we're going to see that it works exactly the same way. Let's see. So let's look at the average gestation times, which is the length that women are pregnant, for a sample of 100 women. If we imagined all possible random samples of 100 women that we could take and looked at a histogram of the sample means, we want to know what shape would it have, okay? Well, if we think about those conditions, obviously one woman's gestation period is going to be independent of others, so we're good on the independence condition. 100 women is less than 10% of all women who have had babies, so we're good to go there. And then for means, remember, we just need a sample size that is greater than 30 to verify that it is big enough. And here we've got 100 per sample, so we're good to go. So we have an approximately normal curve because all of those conditions check off. So now we just have to describe what that would look like. So now we might want to know what would the center of the histogram be and what would that standard deviation of our normal curve be. Well, 9 months is pretty typical, and that is about 266 days. So the center of our sampling distribution is actually going to be the same as that. It'll be 266. And let's just say that our standard deviation of the 100 women is 10 days. Well, to find the standard deviation of our sampling distribution, this is right off our formula sheet. We take our standard deviation divided by the square root of our sample size, or 100. So we'd take 10 divided by square root of 100, and that would give us a sampling distribution of 1 day.